Today we're going to be talking about quadratic functions. Now, quadratic functions are a special type of a larger class of functions called polynomial functions. So let's start with the more general class and then talk about specifically the quadratic functions, which are our topic for today. So a polynomial function is a function of the form f of x equals, and then x to the n, an times x to the n plus an minus 1, x to the n minus 1, etc., plus a1 times x plus a0, where n is a non-negative integer and an is not equal to 0. In other words, a polynomial function is a function that can be described using a formula that is a polynomial. We've actually already spent a lot of time looking at polynomial functions of one kind. The polynomial functions are sort of categorized by the degree of their polynomial. So the value of n is the degree of f. So for instance, if we have polynomial functions of degree 1, they are of the form f of x equals a1x plus a0. And this is actually a type of function that we've looked at a bunch. These are linear functions. And we know that the graphs of these functions are lines. And in fact, when we write it out this way, a1 is the slope of that line, a0 is the y value of the y-intercept, and we've done a lot with these. Polynomial functions of degree 2 look like f of x equals a2x squared plus a1x plus a0, and these are called quadratic functions. So this is going to be our subject for this video, understanding functions that have a formula of the form that is a degree 2 polynomial, that is a quadratic function. So we are going to be looking at functions like this and understanding their graphs, how we can graph them out, some of their properties, including where they have local maxima or minima, as well as their domain and range and so forth and so on. So there are two different forms that a quadratic function can take. We've got this one, and I'm going to switch to A, B, and C rather than A2, A1, and A0. This is called the general form of a quadratic function. There's another form that we sometimes use, which looks like this. It's the form a times x minus h squared plus k, and this is known as the standard form. Now, we will see a little bit later how we can translate back and forth in between the general form and the standard form. For the most part, most of what we use quadratic functions for just uses the general form. Most of the time, the general form is the more useful form of the quadratic function. But we are going to use the standard form in order to start looking at how we actually graph a quadratic function. So that's our first goal, is to understand the graph of the function f of x equals a times x minus h squared plus k. And in order to do this, we're going to go ahead and look at a couple of specific examples so that we can see the patterns and describe the general conclusion. So let's take a couple of examples. I want f of x is equal to 2 times x minus 1 squared plus 3, and I want to look at the equation g of x equals negative 1/3 times x plus 2 squared minus 4. And let's go ahead and get ourselves a grid here to work with. Now, the thing to notice about these both of these functions here and their formulas is that they are transformations of our basic x squared graph. So these are both transformations of the function given by y equals x squared. And so let's identify what is going on here. So in this case, for the function f, we have that f of x is equal to, then we have a 2 on the outside, then we have an x minus 1 inside, and then we have a plus 3 on the outside. And each one of these does a particular transformation to the graph of y equals x squared. We know that the minus 1 inside is going to cause the graph to shift right by 1. We know that the plus, let's work outwards. The 2 here is going to stretch everything vertically by a factor of 2, and the 3 on the outside is going to shift everything up by 3. All right, let's do the same analysis over here on g of x, and then we'll actually move to another slide in order to graph things out. So we've got g of x is minus 1/3 times x plus 2 squared, and then minus 4. And so here we're looking at 4 different transformations. First, we've got the plus 2 on the inside, which tells us that we're going to shift left by 2 units. The 1/3 on the outside says that we're going to scale or compress vertically. By a factor of 1/3. Now the negative out in front says we're going to reflect across the x-axis, and the minus 4 on the outside says we're going to shift down by 4. So let's go ahead and look at these 2 functions. Actually, we'll do the f function first and see if we can spot the patterns and how we can look at the formula in the future and graph the function more efficiently. So if I make my tick marks like this, 1, 2, 3, then I will start by graphing the original y equals x squared function in blue, and we know that goes through some specific points. We know it goes through the points 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4. I realize I missed the negatives on these ones over here. And so, our function, we're going to shift right by 1, and then we're going to stretch vertically by 2. We're going to multiply the y value by 2 and then add 3. So, putting all these things together, I realize I'm going to need somewhat more space here, so let me go ahead and do that. All right, so for instance, the point 0, 0, when we move it to its new place, we're going to shift it to the right by 1, and that will put us at the point 1, 0. Oops. Sorry about that. All right. So the point 0, 0 will go to the point 1, 0 after the shift right by 1. But then we're going to stretch vertically by a factor of 2. We're going to multiply the y value by 2. But that just goes back to 0. But then we're going to shift up to 3. And so that's going to put the point 1, 3 on the graph. Then we're going to take the point 1, 1. That's going to shift over by 1 to the point 2, 1. And then we're going to multiply the y value by 2, getting us to the point 2, 2. But then shift up by 3, getting us up here to the point 2, 5. And then similarly, if we look at where the point negative 1 goes, that's going to come up here to the point 0, 5. So when we graph out our new function, we get something like this. Here's f of x equals 2 times x minus 1 squared plus 3. Now, what I want to notice here, what I want to point out for us to compare to the next example are the following 3 pieces of information. The first is the vertex. Now, the point that's right at the top or bottom of the parabola that's defined by a quadratic function is called the vertex. So it's either the highest or lowest point of the parabola. So in this case, the vertex is at the point 1, 3. Next thing I want to note is that the parabola opens upward. And then I want to note that we have some symmetry involved in this parabola. Now, the original parabola x squared was symmetric around the y-axis. Our new graph, our red graph, is not symmetric around the y-axis, but it is symmetric around this line x equals 1. It's symmetric around the vertical line that goes through the vertex of the graph. So let's take this. Let's do our other example and see if we can spot the differences. So our previous example was g of x equals negative 1/3 times x plus 2 squared minus 4. So let's look at this one and see how graphing this goes. Now for this one, I'm actually going to need a little bit more space below the x-axis because it turns out this parabola is going to open downward. So let's take our points again. I'll label the axes here. So I got 1, 2, 1, 2, 3. Oh, I didn't get those points quite right. I'll fix those. -1, -2. This point should be here, and this point should be here. All right, so here's our original graph. And we've got the point 0, 0, and the point 1, 1, and the point -1, 1. And I'm just going to sort of trace out what happens to each of these with our various transformations that we got over here. So the point 0, 0. So the first thing that we're going to do is we're going to shift left by 2. And if we take the point 0, 0, shift left by 2, we get to the point -2, 0. So that gets us to this point right here. Then we're going to compress vertically by a factor of 1/3, which means we're going to multiply the y-coordinate by 1/3, but for this problem, that just gets us back to 0. Then we're going to reflect across the x-axis, which means that we're going to multiply our y value by a -1, but of course, in this case, that just gets us back to 0. And then finally, we're going to shift down by 4, which will give us -2, -4. So that gives us -1, -2, -3, -4. So the vertex in the original parabola was at 0, 0. The vertex in the new parabola is going to be at the point -2, -4. And this is our vertex. All right, so let's see what happens to the others. So if we look at the point 1, 1, we're going to shift left by 2, so that'll go to the point -1, 1. If we compress that vertically by a factor of 1/3, that's going to give us 1, 1/3. We multiply by 1/3. Then we reflect across the x-axis. So currently we're at this point right here. We're going to reflect across the x-axis, which means that we're going to multiply the y value by -1. So we get to the point -1, -1/3. And then finally, we subtract 4. We shift downwards by 4. So we get to the point -1, and then -1/3 minus 4 is -13/3. It's -4 1/3. So that gets us our second point here. So we get that we have -1, -13/3. And then finally we can do the same thing with -1, 1. It's going to go similarly. We shift left by 2 to get -3, 1. We compress vertically to get -3, 1/3. We flip around the x-axis, which gets us to -3, -1/3. And then we shift down by 4 to get -3, -13/3. So that gets us a point over here where we've got -1, or -3, -13/3. And so what we see here in this case is that the parabola, instead of opening upwards, is opening downwards. Now again, I want to look at the same pieces of information here as I did before. First of all, we have our vertex at -2, -4. We see that we have an axis of symmetry here at x equals -2. The green graph of our function is symmetric around this, this vertical line. And we have that the parabola opens downward. So if we compare what we did in these last two examples, we can see some patterns. First of all, we can notice that the vertex in both of these examples was obtained by shifting the vertex of the original y equals x squared function, which was at 0, 0. And so it's always the two shifting numbers, in this case the 2 and the -4, in the previous case the 1 and the 3, that moves the vertex. Now the vertex also determines this line of symmetry. The parabola that we always come up with is determined by the, always has a line of symmetry, and that line of symmetry is always the vertical line passing through the vertex. Finally, the direction of the parabola depends on whether the number out in front is positive or negative. With our original function, or with our first function f, we see that our leading number of 2 was positive, which means that we never wound up reflecting anything across the x-axis. Our function y equals x squared started off opening upwards, and our translated function ended up opening upwards. However, our function g has a negative coefficient in front of the x term, and that winds up reflecting the graph across the x-axis, making everything open downward. So let's summarize this information that we have to see how we can take the standard form of a quadratic equation and quickly graph it using these principles. So let's look at the graph of a quadratic function in standard form. So we've got the function f of x equals a times x minus h squared plus k. This is the standard form of a quadratic equation, a quadratic function, I should say. So a few points that we have. The vertex is at the point h comma k. This function is a shift or a transformation of the original parabola x squared function, where we've shifted to the right by h and up by k. And therefore the vertex of the new parabola is at the point h comma k. We have an axis of symmetry at the point, the x equals h. So this is the vertical line which passes through the vertex, and the function has that line as an axis of symmetry. And then number 3 is that the parabola opens up if a is greater than 0 and down if a is less than 0. So these 3 things by themselves allow us to get a general idea of what the graph of a quadratic function looks like. Now, it's not quite enough to get us the full graph. So in order to graph the quadratic function, so to graph f of x equals a times x minus h squared plus k, we want to find the vertex and one other point I should be more specific than say one other point. We want to find the vertex. We want to find the intercepts. That is, find the places where the graph intersects the x and y axes. We want to find the x-intercept and the y-intercept. additional points if necessary. They may be necessary because the intercepts in the vertex might not be enough. You want at least 3 points in order to graph the function properly. Additional points if necessary using symmetry to help. Then connect the points smoothly. Now this seems like this might seem like a lot, but the fact that the quadratic functions sort of all behave the same way means that with a little bit of practice you can become very quick at doing this. Let's see an example. So let's graph the function f of x is equal to 2 times x minus 2 squared minus 4. So the first thing that we want to do is to identify the vertex. And so we always want to realize this in the form a times x minus h squared plus k. So in this, we have that a equals 2, h equals 2, and k equals 4. So in particular, that tells us that the vertex of this parabola will be at the point 2, 4. I'm sorry, k is negative 4. I dropped a negative here. So that means that the vertex is at 2, negative 4. So we want to start there. So we always start with the vertex 2, negative 4. Now we know already that because a is positive, the parabola opens upward. So we know that it's going to open upwards, but there are lots of parabolas that have this vertex that are narrower or shallower. So we could have all sorts of parabolas with this vertex. So let's find some more points. So let's find the intercepts. The y-intercept is always easy to find because to find the y-intercept, we just need to find the y value that goes with an x value of 0. So the y-intercept, we just find that f of 0 is equal to 2 times 0 minus 2 squared minus 4. So we get 2 times negative 2 squared minus 4. Negative 2 squared is 4, so we get 8 minus 4, which is 4. So the y-intercept of this graph is at 0, 4. So there's another point that's on the graph. Now here's where we can use some symmetry. And let's do this before we move on to the other intercept. We can use the fact that we have a line of symmetry that is a vertical line that goes straight down through the vertex, x equals 2, to find another point that's on the parabola. And the way that we do that is we look at the point 0, 4 we've got, and we see, okay, well that's a distance of 2 from the line of symmetry horizontally, which means that if we go a distance of 2 in the other direction of the line of symmetry, we will get another point that is on the graph. So because of the symmetry of the parabola, since the point 0, 4 is on the graph, and the graph is symmetric around the line x equals 2, the point 4, 4 will also be on the graph. So now let's get the x-intercepts. we want to set f of x equal to 0 because the x-intercepts are where y is equal to 0, where the output of the function is equal to 0. So that means that we have 2 times x minus 2 squared minus 4 equals 0, and we can solve for x. So we can add 4 to both sides, get 2 times x minus 2 squared equals 4. We can divide both sides by 2 and get x minus 2 squared equals 2, which means that x minus 2 is going to be plus or minus the square root of 2, which means x is going to be 2, if we add 2 to both sides, plus or minus the square root of 2. So this means that in this case, our two x-intercepts are not whole numbers. And in fact, they're irrational numbers. And we have two of them, 2 plus the square root of 2, 2 minus the square root of 2. Now, one thing that you can do here to help yourself out is to use a calculator. And you can see from a calculator that the square root of 2 is approximately 1.4. And approximately 1.4 is all we need if we're just sketching out a graph like this. So if we have x equals 2 minus the square root of 2, that's approximately 2 minus 1.4, which is 0.6. So this means that the point 0, the number 0.6 is between 0 and 1, which means that we can put a point approximately there. And that's where the point 2 minus the square root of 2 comma 0 will be. And that'll be one of the x-intercepts of the function. And so our other number is 2 plus the square root of 2, which is approximately 2 plus 1.4, which is 3.4, which means that our other point, our other x-intercept, will be here, between 3 and 4. So this will be our point 2 plus the square root of 2 comma 0, and that gives us points on the parabola. All right, so this is the general a general strategy that you can use in order to graph a parabola when it's written in standard form. Now, before we move on to considering how we handle functions that are written in general form, I want to notice some things that we can tell about a function based on its graph. So we can see from here that the vertex of this graph is in fact a minimum. And it's a minimum because the parabola is opening upwards. In our previous example with the parabola that's opening downwards, let's look back at that, you'll notice that the vertex here is a maximum. It's a point that's higher on the parabola than any point near it, or indeed any other point on the parabola. And so, in fact, the vertex of the graph is always going to be the maximum or minimum, depending on whether the parabola is opening down or opening up. We can, of course, also use this to determine the range of the function. And furthermore, the domain of these functions are just all real numbers, because we can plug any number into a polynomial and get something out of it. So next I want to summarize what we can tell about a function once we know the vertex and which direction the parabola goes. So a quadratic function with vertex at h comma k has the following properties. First of all, no matter what, the domain is all real numbers. The domain of a quadratic function is all real numbers. The range is going to be from k to infinity if the parabola opens upward, and from negative infinity to k if the parabola opens downward. And the point h comma k is a minimum if the parabola opens upward, a maximum if the parabola opens downward. We're going to use this in applications in order to solve problems where we're trying to find the maximum or minimum value of something. All right, so now let's talk about how to handle quadratic functions that are in general form. So the general form of a quadratic function, remember, looks like f of x equals a x squared plus bx plus c. This is the form that we most often encounter quadratic functions. Most of the time we don't encounter a function already factored out so nicely as we had it before. So what we want to do to understand how to handle this is to figure out how to rewrite this function into a form that looks like the standard form that we had before. And the technique that we're going to use to do this is the technique of completing the square, which is in fact the same technique that we used when we were looking at the quadratic formula and trying to establish that. So let's see how this goes. I'm going to start off by working things out in the abstract here, but then we'll give the key, and we're going to be able to turn this process into a very quick formula that we can use to find the vertex of the quadratic function given here. And once we have the vertex, that really tells we can get all the rest of the information that we need very quickly. So we're going to complete the square. And so this is going to involve taking some algebraic manipulation of the expression ax squared plus bx plus c. So first thing I'm going to do is I'm going to factor a out of the first two terms only. So if I factor a out of ax squared plus bx, I get x squared plus b over ax plus c. Now this looks a little weird because there wasn't an a visible in the bx expression there. Remember that a and b are both numbers. Furthermore, a is required to be non-zero. Whenever we have a quadratic function, a has to not be 0, which means that we can divide. If you want to double check that you've factored correctly, or that I've factored correctly here, the way to do that is to distribute the a back through to make sure that you get the original expression back. So if I multiplied a in here, I would get a times x squared is ax squared, and then a times b over a is b. And so this gives us that this factorization is correct. So then I'm going to use the completing the square trick, which means that I'm going to take a times x squared plus b over ax. And now I'm going to add a term here that will guarantee that the three terms x squared, b over ax, and the next term I'm going to write all factor as a perfect square. And it turns out that the number that I need to make that happen is b over 2a squared. It's taking half of this, half of the number b over a, and squaring it. So we get b over a squared here. But of course, if I want to add b over 2a squared, I need to subtract b over 2a squared in order to cancel it out. I'm not allowed to actually add anything, so I'm just going to add 0. But I'm going to add 0 in a clever way by adding and subtracting b over 2a squared. So now we're going to split things up. We're going to take the first three terms in this parenthetical expression by themselves. So we'll get a times x squared plus b over ax plus b over 2a squared, and then minus a times b over 2a squared plus c. Now, this technique of completing the square means that we can factor this trinomial. X plus b over ax plus b over 2a squared is x plus b over 2a, that whole quantity squared. Now, working out the stuff on the right, we have minus a times, we get to do b squared over 4a squared plus c, and rearranging all of this, rearranging the right hand a little bit, we get a times x minus negative b over 2a. I'm doing this so that it matches up with the standard form from before. Sorry, I need to move this over here. Plus c minus b squared over 4a. One of the a's canceled here in the product. So what this means is that if f of x is equal to ax squared plus bx plus c, another way of writing that is to write it as a times x minus negative b over 2a squared plus c minus b squared over 4a. And the amazing thing is that we can actually recognize this as being the standard form of the equation of a polynomial, of a quadratic function. So what this tells us is that we can match up these numbers. We get that h is equal to negative b over 2a, and k is equal to c minus b squared over 4a. All right, so what does this mean for us? It means that the vertex of f of x equals a squared, or a x squared plus bx plus c is at the point negative b over 2a, comma, c minus b squared over 4a. Now, it turns out that in practice, we don't actually memorize both of these. In practice, we only memorize this one. And this negative b over 2a expression is what we use in what we call the Vertex Formula, which I'm going to write down next. The point is, the good thing that we see out of this is that we can determine the x-coordinate of the vertex very quickly just from the general form of the quadratic equation. So Let's look at the vertex formula. The vertex formula says that the vertex of the quadratic function f of x equals ax squared plus bx plus c is negative b over 2a comma f of negative b over 2a. So, in other words, what this means is that to find the vertex, we first just compute its x-coordinate as negative b over 2a, then plug that number into f. And when you do that, that will give you the y value of your vertex, and then you will have it. Let's see how this actually plays out with an example or two. Let's graph the function f of x equals 3x squared plus 12x minus 1. So, for the vertex formula, we have that the x-coordinate of the vertex is equal to negative b over 2a. Now, b is the coefficient of x, so that's 12. And then we have 2a is the coefficient of x squared, so that's going to be 3. So we get negative 12 over 2 times 3. 2 times 3 is 6, and so this whole thing becomes negative 2. So that's the x-coordinate of the vertex. So, to get the y-coordinate of the vertex, we plug the x-coordinate of the vertex into the function. And we get f of negative 2 gives us 3 times negative 2 squared plus 12 times negative 2 plus 1. So 3 times negative 2 squared is 3 times 4. 12 times negative 2 is minus 24 plus 1. And now 3 times 4 is 12. 12 minus 24 is negative 12 plus 1 is negative 11. So that means that the vertex of this parabola is at the point negative 2 comma negative 11. We also see that the parabola opens upward, which means that we can sketch out approximately what this graph looks like already. And if we don't need anything super precise, then we can, a lot of times we can get away with just this. This gives us all the information that we need. So we've got a parabola looking approximately like that, and it doesn't have to be too pretty. Now, a lot of times we do want some more information, and so a lot of times the best thing to do is to find the y-intercept and use some symmetry. So for the y-intercept, we just have to plug 0 into the function. Now f of 0 is really easy to figure out when the function is in general form, because all of the terms except the last one are just 0. So we have that f of 0 is equal to negative 1, which means that we can plot another point here, 0 comma negative 1, that's on the graph. Furthermore, by symmetry, we have that the graph is symmetrical around the line x equals negative 2, because that's the coordinate, that's the x-coordinate of the vertex. So the vertex formula, negative b over 2a, not only tells you the x-coordinate of the vertex, but it also tells you the line of symmetry for the parabola. And so what that means is that if you take a point that you know is on the graph, then there's going to be a corresponding point on the other side of the graph, the same distance away from the line of symmetry here. So the point 0, negative 1 is 2 units to the right of this line, which means if we go 2 units to the left of this line and get the point negative 4, negative 1, that point will also be on the graph. So let's sketch that in. And so we can graph things out that way. And again, we can see from the function that the parabola opens upwards, and again, that's because of the leading coefficient. It's because of this the coefficient of x squared, the a in our problem. Because a is positive, this parabola opens upwards. And that's the basic idea behind finding the vertex of a function that's given in general form. Now, again, once you know the vertex, you know lots of things about the fact that the vertex is either a maximum or a minimum. It determines the range of the function and all the other things that the vertex gives you that we mentioned earlier. Let's look at an application for how we might use this process of finding the vertex to solve a real-life type problem. So, let's suppose a farmer is enclosing a divided pasture next to a cliff, as in the figure. And so, figure is we've got a cliff right here, and we've got some fences that we're going to use to enclose a pasture, but the pasture has a couple of divisions in it. If the farmer has a total of 1,200 yards of fencing, what is the total, what is the maximum total area? He can enclose. So this is another good example of, or rather our first good example of how we can use finding the vertex of a quadratic function to solve an optimization problem. An optimization problem involves finding the best of a bunch of possible scenarios for a given way of measuring what's the best. In this case, we want the maximum total area here. Now, of course, there are lots of ways that the farmer could enclose this pasture, lots of different lengths of sides that he could use. First of all, we can, of course, assume that he's going to use all of the fencing. If he doesn't use all the fencing, then he's not enclosing the maximum area. He can always go a little bit bigger. So we know he's going to use all the fencing. We just want to know what's the maximum he can get. If he makes it too skinny in one direction or another, he's probably not being real efficient with his materials. So let's solve this problem. So let's let x be the width of the enclosure. So if we do that, by width, I mean this distance right here. So the right-hand fence here is going to take x yards of fencing. So we want to measure this in yards. Now, if we do that, because we've got this rectangular pasture here, which I didn't specify in the problem here, I suppose, but will be specified on a homework or quiz or anything like that. So because this is rectangular, all these other fences are going to have the same length. So we have x yards used for each of these 4 fences coming straight out from the cliff. Now, what that means is that the amount of fencing we have left for the fence on the bottom, we can compute. We know we have a total of 1,200 yards of fencing, and we've already used 4 times x yards of it. And so the amount that we have left is 1,200 minus 4x. So if x is the width of the enclosure in yards, then we have that 1,200 minus 4x will be the length of the enclosure. So that means that the total area of the enclosure is length, 1,200 minus 4x, times width, x. So in fact, let me let f of x be 1,200 minus 4x times x. We can rewrite this, if we distribute the x through, as 1,200x minus 4x squared. And if we write it this way, we can see that this is in fact a quadratic function. This is a degree 2 polynomial that is being used as the formula for the function f. Furthermore, we can see that the coefficient of x squared is negative. Now, even though we've written our formula this way, this number, -4, is still going to count as our a from before, because it's the coefficient of x squared, even if they're written in a different order. And the coefficient of x is going to be a b. So, since the coefficient of x squared is negative, the graph of f is a downward opening parabola. So in particular, that means that the vertex is a maximum. So the graph of f is going to look, I don't know exactly what it's going to look like, but it's going to be a downward opening parabola, which means the vertex, wherever it is, has to be the maximum. So let's go on to another page and figure out what the vertex of this function is. So we've got f of x is 1,200x minus 4x squared. So we use the vertex formula. We know that the that the x coordinate of the vertex is -b over 2a, which is going to be negative. Now b here is 1,200, remember, because b is always the coefficient of x. And then we have 2 times a. A is -4. A is always the coefficient of x squared. And so we get -1,200 over 8. And so, well, we get, I'm sorry, over -8. Almost missed that negative there. That wouldn't have made any sense. Which is 150. So that tells us that the vertex, i.e. the maximum, occurs when x equals 150, i.e. when when the pasture is 150 yards wide. Now, if we look back at the problem, we see that the problem did not ask us for the dimensions of the pasture. It asked us for the maximum total area. Now, the function f is in fact giving us the maximum area of, or is in fact giving us the area of the pasture for given values of x. So if I want to know what the maximum value of the function is, I just need to find the y value of the vertex, which is the output of the function when x is or at the vertex, the maximum value. So this tells us that the maximum area is f of 150, which is 1200 times 150 minus 4 times 150 squared. This is something that a calculator can definitely help you with. In this case, we've got 180,000 minus 4 times 22,500. So you work this out. Get 90,000 here, and so we get 90,000. Now the area in this case was being measured in square yards because we were multiplying two yard distances together. So our answer, our final answer, will be that he can enclose a maximum of 90,000 square yards. And that's how we can use the vertex of a parabola in order to solve an application problem. We can also use this to find minimum values for things, in which case, for it to work, our function has to have a graph that is an upward opening parabola, of course, so that the vertex in that case will correspond to the minimum values of the function.